Okay, so it's recording. So just as usual, everything's up here. When you get a chance, please complete the course survey. It's online. There should be a link that should come to your email. Your feedback is very useful for me, so please feel free to do that. Or, of course, you can also email me directly if you have any questions, concerns, and comments. Just a quick point before we start is that the report that's due is one per team, not per student, and it is basically the same as what you would do in a presentation, but in a written form, and it has to be less than 3 pages long. Okay, so I sent an email with those instructions. Hopefully you received them. And Friday you can email it, submit it on Canvas, whatever is easier for you. PDF or something is fine. Okay, so let's jump right in. Are there any questions before we start? Okay. I know you have a question on assignment 4, we'll defer it back to later. Okay, so today's goal was to go through 2 topics. The first topic is the idea of measurements in photovoltaics, and in particular, measurements that are related to optics. So that it is very useful to know if you ever go work in this industry, because some of this, can we turn that up? Just give it a minute. Step away. It's very useful because measurements tend to be fairly complicated, and there are a few things that you need to look out for, which I will point out. So, first of all, what are we trying to measure? What we're trying to measure first, for a solar cell, of course, the electrical characteristics are the most important thing. It's a PN junction, as we all know. We reverse bias it, right? So that means the PN junction has a negative voltage applied to it. And typically, if you look at the curve, I want to turn this off. If you look at the voltage, it's or the current. You look at the reverse bias current under the illumination conditions. So you have a reverse bias PN junction. You shine light on it. Barriers are created. Current flows. Okay, which means that the current flow is essentially opposite to the applied bias. So you always treat this as a curve which looks like this. If you do it in a conventional sense, current is negative as you apply the bias. This is reverse bias. And you will see a curve which looks like this, okay? But let's look at this in more detail. And of course, for most of us, we will flip this curve up. So it look like this to keep things similar to what we're used to. So again, we have current here, and then voltage here. So you apply the reverse bias voltage, you shine light at a fixed intensity, you measure the current. Okay? So this red curve is the current voltage characteristics. It looks like that. At 0 voltage, you get a current which is referred to as a short circuit current, ISC. At 0 current, which means when you short the device, when you apply infinite, so there's 0 current, right? There's nothing drawn from it. You get what's called open circuit voltage. So this is when you have an open circuit. Those 2 numbers are very important, and if you look at a solar cell, pretty much that's what's characterized. Of course, if you take the current and multiply with the voltage, you can plot the power. So this is power versus voltage, and you'll see something which looks like that, which shows a peak value, and this is the maximum power you can get out of the system. And it also tells you where you want to operate the solar cell at. So that's the amount of current that you really want to get out. That corresponds to the maximum power you can get out. And you can do this by balancing the load, as some of you who are electrical engineers have probably done in the past. But for us, it's not so important from an optics point of view, but just be aware that this is what happens. Another important metric that we have to be aware of is something called fill factor. This fill factor is essentially defined as the ratio of the area of this pink rectangle, which is right here, divided by this purple rectangle. Okay? And mathematically, simply, the area of the pink rectangle is, it's the opposite. So the area of the purple rectangle divided by the area of the pink rectangle, so it's always less than 1. The area of the purple rectangle is the peak current multiplied by the peak voltage, or the voltage and current corresponding to the peak power, divided by the short circuit current multiplied by the open circuit voltage. This is a measure of how good your solar cells in terms of converting sunlight into electricity. So it's a nice number to have. Of course, you want this to be as high as possible. 100% would be ideal, but that never happens. 100% means that you should have a curve which is non-linear, which is not, it doesn't exist in real life. Now, efficiency is the most important metric to some extent for us. That is defined as output power, maximum output power. Typically, you do this at a peak value, which is not necessarily fair. You're not operating at that value, but as a specification, this is what most people do. Output power at the maximum point divided by the input power. That can also be written as Pmax. Sorry, this can also be related to the fill factor, which is given by the Pmax divided by VOC times IC, which is exactly the same. So efficiency and the fill factor are basically proportional. If I have a very high fill factor, that means I also have a high efficiency. Now, when you do these measurements, of course, you need to use standardized conditions because everything affects, as we know, everything affects the solar cell. Spectrum, cloud cover, diffuse light, direct light, whatever. So these are the standards. You don't need to, you just need to aware that there are standards, particularly in the intensity, because I'll come to this later on. The intensity, in other words, the brightness of the sun matters on the efficiency of the device, which is a little bit counterintuitive. But it does matter because of some physical effects. Which we don't have time to go into. So that intensity choice is very important when we use it for standardized testing. You do it either on Earth, terrestrial, on Earth with concentration, which means that you get over 1,000 watts per meter squared, or you also do this in space, of course, with satellites and so on. So you do a slightly different measure. Spectrum we've already talked about. There are various standards. We usually talk about AM 1.5, AM 0 in space, and so on. We'll come back to that. Temperature is very critical as well. Different materials respond differently at different temperatures. High temperatures usually are bad for silicon, but high temperatures could be very good for gallium arsenide. So it really depends on the material. So you have to be careful, but for standardized testing, you have to specify what temperature is measured at. Okay, so for for measurement of efficiency, we have to be careful how we define the input power and output power, particularly for concentrator systems. And of course, the definition is common sense, but sometimes it's difficult to ascertain the aperture size. This is how we point out. So for a non-concentrator cell, this is relatively simple. You take the entire area of the cell into account, which, by the way, includes the contacts and grid lines and so on. In other words, if you look at a solar cell, you will see not just the silicon, but you also see all those metal lines. You're supposed to include all those in the area. And that's the standard. And that's correct, because that's what you have, and that's the amount of area you have to collect. For a concentrated cell, of course, it's more complicated because you have something on top of the cell. So you have to be careful. So if you have a CPC, it has to be the input aperture of the CPC. If you have something more complicated, like the polychromat that Nabil talked about, you have to take the input aperture of the polychromat, or whatever else that you have. So, which is common sense, but in complicated systems, this can be tricky we have to be careful how you do. The area illuminated or the input aperture is important. Now, calibration is also quite important, primarily because the incident power or the insolation, the denominator of the efficiency, cannot be measured very precisely unless you have very expensive equipment. So to avoid this, so we don't need to, if you're installing it on a roof, someone doesn't have to bring expensive equipment, you can use like a reference cell. This reference cell means basically it's a photodetector, usually a silicon solar cell also, which is calibrated very carefully such that its reading corresponds to the exact measurement. So it's calibrated. So incident power, Pn, has to be calibrated carefully. This is done usually using a reference cell whose short circuit current has been calibrated with respect to a known reference spectrum. Which means that you can buy this calibrated cells, which has been very carefully calibrated in a lab, but if you take it outside and do the measurement, it will give you a pretty accurate measurement. In our lab we actually use it because to calibrate the cell is time consuming. So that's something also to be. Now, AM 1.5, we've already talked about this, but just to review ourselves, the location of the sun with respect to the solar cell is important when we do these measurements. So typically we talked about AM 1.5, AM standing for air mass. This corresponds to something like that, approximately between the zenith and the horizon. Okay, it's defined around 48.19 degrees because that's when you get this air mass of 1.5, which is the 1.5 amount of optical length compared to the zenith. Okay. The relative optical mass, if you want to compute it in any other location, is secant of theta. It's 1 over cosine theta. It goes to infinity here, obviously, and it goes to 1 here. But in almost all cases, we deal with M1.5. So that's all we need to really know about. Now, the spectrum, of course, is very, very important when we try to measure solar cells carefully. And you got a taste of this with Nabil's lecture when he talked about spectroscopy. So you can imagine a solar cell, if I put it outside today, under cloudy conditions, will give me a very different response than if I put it tomorrow under sunny conditions. Not just because you have more light coming in, I can normalize for that. Let's say I put a filter to adjust for the brightness, but because the spectrum itself is different. In other words, there might be more blue photons than green photons, for example, or more blue photons than red photons, for example. And this shaping of the spectrum can also affect the response of the solar cell because every photon gives a there's a different probability for a given photon to generate an electron-hole pair in a semiconductor. And this will come to is what's referred to as a quantum efficiency. So before we talk about that, what this means is that when we do measurements with a solar cell, we have to be careful about what the spectrum is going in. So you need to actually know what it is. So of course, to know the spectrum, you need to have expensive equipment. So typically, you don't do that when you are trying to install solar panels on the field. So you have something calibrated, some measure of calibration. And the way it's done is relatively simple. So you adjust the if you have a test cell that you're measuring under some reference spectrum, you take the short circuit current density, you scale it based on this simple expression. In other words, this is the test cell under some source spectrum divided by m, which is a spectral mismatch factor, which is defined here. We'll come to that in a second. Multiplied by this ratio, which is basically the short circuit current density of a reference cell taken with the reference spectrum divided by taken with the source spectrum. So it's just scaling the spectrum. It's not exact because to do it exactly, you have to actually do an integral over the spectrum. This is just an approximate, but it's a relatively good approximation. Now, the spectral mismatch factor is simply something that gives you an average ratio between the source spectrum that you're trying to measure, let's say some light out in the field, and some reference spectrum that you know very well that you've calibrated very well. And it's relatively simple. You take the source spectrum, which is down here in the denominator, E, multiplied by the spectral response of the cell, which is the quantum efficiency, which we'll come to in the next slide, and do an integral. And take it, the reference spectrum, multiplied by the response of the reference cell, and divide them. And you have the cross terms here as well. So in other words, you have the reference spectrum, spectral response of the test cell. So it's a simple scaling, the approximate way to do the actual calibration. The other thing, of course, we have to be wary of is when we do measurements is artifacts. So I'm not sure if Bill mentioned, but when you always do these IV curve measurements, there's all kinds of strange things that can happen. The most common thing that we see if you buy a cell and try to measure it is that instead of seeing this nice nonlinear curve, you see a straight line, which means that there is a huge it usually means that there is a huge series resistance in your circuit. Okay? And these things you have to be aware of and needs to be taken care of. One of the important things is hysteresis. So that when if you imagine you do this measurement, you have a silicon solar cell, you measure this, you bias the voltage, you measure the current, you get this curve. And you try to go back. In other words, you try to reduce the bias, and you see a different curve. So it gives rise to this hysteresis, and that's a problem. This basically means that some of the carriers are either trapped or not being generated. In this particular case, that means they're trapped in the forward direction. And this is not good because you could, you might be changing in an actual solar panel, you might be changing the bias slightly. This is, by the way, what a smart inverter does. It changes the bias slightly to get the maximum juice out of the solar. So if you're doing that and you don't know exactly what the response is, because these are two possible things that can happen in terms of resistors, that's a big problem. That means your power electronics, your control circuitry for your power electronics will not work properly. So that's a problem. So we need to be careful about how to, about the situation and how to deal with it. To avoid this, in terms of measurement itself, you can just measure it slowly. You allow all the carriers to relax before you actually measure it. Or you can just measure the current at a fixed voltage, which is not good for IV curves, but at least you can get a measure of the performance of the cell. Fixed voltage could be open circuit voltage. In an actual cell, you do something called light soaking. So this is something I actually saw when I visited one of the factories for a SIG cell in the Bay Area. So what this means is that if you take a solar cell, so the current voltage curves change with exposure to light. In other words, if you take a brand new solar cell that you just made and put it under, you measure its IV curve, and then you put it out in the sun, measure it for an hour or so, and then you measure its IV curve again, they will look different. And the mechanism for this, by the way, is not well understood. But this is not good because you have variation. Like if you put your panel up, and that's never good. You want to have something as steady as possible because remember, these panels have to last for 25, 30 years. They have to keep pumping energy out, right? So this is just an example which shows a cadmium sulfide CIS, copper indium diselenide cell. As you increase the exposure to light, you can see the efficiency. So this is initial exposure to light. It's after 2 hours of exposure to some light. Efficiency goes from 6.6 to 6.9%. So what happens really, it's interesting in 6 chalcogenide cells that you can buy like from First Solar, for example, which is a big company who sells cadmium telluride cells. What they do is after they manufacture their cells, they actually leave it out in a light soaking chamber for several hours before it's shipped out. This is to stabilize the cell. The physics is not quite understood, right? It kind of looks like this. I saw something like this in one of the factories I visited. The other thing, as I mentioned before, is the series resistance and contact resistance. In other words, when you try to measure a cell, of course you have to contact it, and there's always some contact resistance, not perfect. And that always shows up as some deformity in your IV curve, and you have to be careful about this. You can do 4 probe measurements as because of your electrical engineers know, basically a differential measurement. Not so important, it's possible to do. You can get very precise results with a slightly better equipment. So just be aware of it. So those are on the measurement side for solar cells. On the other hand, there's a lot of optics and optical engineering involved in the instrumentation itself. So let's talk a little bit about this, and you should be aware of what is available and in terms of what kind of optical designs go into it. There are a few different things here that we'll look into. First, for the electrical measurements, we already saw this, so I'm going to skip that. This is basically the same. I'm going to skip that video. It's important. The first thing is a solar simulator. So when you measure solar cells, you don't always want to rely on the sun, right? Because every day is different. It's cloudy and so on. It changes. So you want to have some kind of way to simulate the sun in a lab, which is repeatable. So every day you do this measurements, it looks the same, right? And this is what's called a solar simulator. A lot of people build their own solar simulators. In my lab, we have our own. We built from scratch. A lot of labs just buy them. In factories and companies, when you do this, you buy this. And this is what it looks like in a very basic terms. There's a lot of optics inside it, and let me point this out. Let's start with the working plane, which is right here. This is where you put the solar cell. So put right here, and you measure the IV curves. The shining light from the top. Okay? So light's coming in from the top. They have a collimating lens. Now the sun is really far away, which means that most of the rays of the sun are coming in straight, as we talked about in the class. Basically collimated, they come as parallel rays of that. Not perfectly, but pretty big. Okay, we talked, remember, about the angles of the sun is about 0.5 degree, so it's pretty small. So that's what that collimating lens does. It tries to make it as parallel as possible. You have a mirror simply to make it more compact, so it's not a very tall thing. And then you have a spectral correction filter. This is basically a filter that takes an artificial source, which we'll talk about, like halogen lamps and so on, and puts a spectral response on the source, which is as close to the sun as possible. It's never perfect. It's actually usually pretty bad. But if you spend more money, you can get it to be as close to the sun as you want. Then you have a shutter, of course, to turn on and off the light, a mechanical shutter, you can see there. Then you have something called an optical integrator. And this is important because most light sources, like the source that we have here, if you look at it close enough, so this is pretty compact, it's about that big. So in other words, if you look at a bulb that is pretty close to a bulb, it looks very non-uniform. You see the shape of the filament and so on. And that's bad, right? Because the solar cell, you want it to be uniformly illuminated. If you have hot spots, that's pretty bad usually. You have some weird physics going on. In fact, you have carrier variations in carrier density, which is not good at all. You end up with much lower efficiency than otherwise. So that's what this does. This is what's called an optical integrator or a homogenizer. It basically takes these non-uniformities and essentially averages them out. And there are many ways to do this. In this particular diagram, it shows an array of microlenses. Microlenses essentially collect light from a small area, pass it through a diffuser, and then a pinhole, and then you get this very clean, nice beam. So in other words, if you place a piece of paper down here, it will look nice and smooth and uniform. Much smoother than this. For example, if you take this projector and look very close, you will see the little pixels on the spatial light margin, so it's not so big. I mean, it depends on the size of the solar cell, of course, right? And then you have another mirror, and then you have the source. Typically, you also have an ellipsoidal refractor to get it as columnar as possible. The source is what we'll talk about next. There are many choices. It depends on the spectrum that you're interested in. The spectrum you're interested in is chosen by the material of the solar cell that you're interested in measuring. If it is silicon, you know you want the visible and infrared, near infrared. If it's germanium, you know you want the visible, near infrared, and not so much the visible, but mostly near infrared and the mid infrared. So it depends on the band that you're looking for. And there are many choices. Xenon is a very common one, cheap, relatively cheap. So this shows the spectrum. So let's start with this bottom curve. So this is a metal halide lamp. So it's like halogen lamps, that the ones used for lighting a bulb. The solid line is the spectrum of the lamp. Because the halogen lamp, you see all these atomic transitions, right? So you see these very sharp peaks because of the sodium has all these transitions, or if it's fluorine or whatever. So you get these sharp lines. And you can compare it to the M1.5, M1 in this case, spectrum shown in the dashed line. So it's not so bad, it's not great, but it's okay. In this case, you are focusing on the UV and the visible. There's no infrared. So this is only really good for maybe silicon, maybe some of the higher band gap materials like gallium arsenide, maybe gallium phosphide. Not so good for, it's not great for silicon because you're throwing away, there's no near infrared. Near infrared is out here somewhere, 900. You can have a mercury lamp. Mercury is great for UV, so you get all these peaks in the UV, which is not great for solar cell because UV will usually create defects in the solar cell. You don't want that usually. Also, it doesn't match the M1.5 solar. The mercury lamp is cheaper, so sometimes it's used. And for maybe if you're interested in UV, for testing some other things like sunscreen, things like that. So, this is a decent one which is QTS lamp, which is a form of tungsten, the tungsten filament lamp, and that's what it looks like. It's very smooth, so you don't see these sharp curves. But and with the filter, you can get something which looks like that, which is kind of an approximation to the same one curve. And you can see it gives you a pretty broad spectrum depending upon the filter you choose. So just be aware that you have many choices for the sources, and it depends on the spectrum primarily, and also the cost usually. So the next thing you want to think about is with the solar simulator. One of the most important things you try to measure is what's called a quantum efficiency. What does this mean? This is basically the spectral response of the solar cell. In other words, if I have a blue photon, versus if I have a red photon, what is the difference in the current that I'm going to get out? This is basically what a quantum efficiency means. Specifically, it's defined as the ratio of the number of charge carriers, which is basically the current, collected by a solar cell. It should really be collected by the leads of the solar cell, so what you can draw out, to the number of photons of a given wavelength incident on the solar cell. So you take one wavelength of light, out how many photons went in, how many electron hole pairs came out. The ratio of that gives you what's called the quantum efficiency. It's an indicator of how good is the solar cell converting sunlight to electricity. Ideally, a solar cell should have high spectral response to the wavelengths where there's abundant number of photons in the incident sunlight. So which is of course green, right? You know, the peaks of the green, so there you want to get as high quantum efficiency as possible. But of course, for a very good solar cell, you want high quantum efficiency everywhere, right? Because you want to collect it. That's impossible, as you saw in the spectral splitting lecture. One way to avoid that is to use spectral splitting optics or use multi-junction solar cells. So there's some interesting physics that we should also be aware of in terms of the quantum efficiency. If you look at a monocrystalline silicon solar cell, which is basically the most common high efficiency solar cell, and you plot the quantum efficiency as a function of wavelength, at UV, very low wave, very short wavelengths, you basically get very lower quantum efficiency because of surface recombination. And what that means is that at the top of the solar cell, there's lots of defects, crystal defects. And these UV photons will be absorbed very close to the top because they're very highly absorbed by the silicon. But those carriers will never make it out to the contacts. They'll just get recombined because of the defects at the top surface of the crystal. So that causes this problem. Out here, you get relatively good quantum efficiency. There's a little bit reduction from 100%, and that's primarily because of some reflection losses, lower Fresnel reflection losses, and small diffusion length, which means that some of the electron hole pairs will make it out to the leads they recombine, which just comes from the basics of solar cells, which we talked about in one of the lectures. At very long wavelengths, you get lower absorption, so quantum efficiency starts to go down. This is because two things. One is mostly because of the reduced absorption, but also because of the rear surface classification. What does that mean? That means at the bottom of the so most of this long wavelength photons will make it through the thickness of the solar cell, is absorbed deeper into the solar cell, which means that they might be close to the bottom edge of the solar cell. And the bottom edge also has lots of crystal defects. So if those carriers are created there, they will get recombined there and will not make it out of the leads. So you lose those carriers. And you have low diffusion length, which is generally dependent upon the crystal structure itself. So like silicon is big, indirect. Actually, crystalline silicon is not bad, but amorphous silicon, for example, has too many defects in the grain structures and your diffusion length of these problems. But not so important for us. Of course, quantum efficiency drops to 0 for wavelengths beyond the band gap. Right? They just not absorbed, as we saw in one of the previous lectures. Ideally, you want something which looks like that, right? 100% everywhere, it drops to 0 after the band. In fact, we wouldn't want that, but that's that case. Now, to measure this, you can measure with the reference cell. So let's just go through it quickly. When all photons are converted and collected as charge carriers, the quantum efficiency is 100%. Photons with energy less than the band gap are not absorbed, so their quantum efficiency is 0%. QE is generally reduced due to recombination. Blue light is absorbed close to the front surface, so recombination of the front surface will affect QE at blue wavelengths. Green light is absorbed mostly in the bulk, so low diffusion length is what reduces that, which is the middle point. At redder wavelengths, surface recombination of the rear surface as well as lower diffusion length will reduce. Basically, what I just said, just reiterate. There are two types of quantum efficiency. One is called external quantum efficiency, which includes the effects of optical losses, such as transmission through the cell and reflection away from the cell. Or you can also, that's what's most commonly measured. The internal quantum efficiency is much harder to measure, but it's very important to understand the fundamental physics of the optoelectronic processes. This refers to the efficiency after you exclude any transmitted and reflected light. Only the absorbed light generating the charge carriers is considered. Again, from our purposes, you don't need to know this much detail, but just be aware of what quantum efficiency is. There are two types of it. And most people talk about quantum efficiency as the external quantum efficiency. The measurement itself is not too complicated. First of all, it depends on the band structure in the semiconductor because that creates the wavelength dependent absorption. Again, energy above the band gap is absorbed, energy below the band gap is not. An absorbed photon creates an electron hole pair, which, if it reaches the electrodes, creates current. To calculate the QE, we need to know the incident power of the cell and its current at each wavelength. Currents produced by the test cell and that of a calibrated photodetector are measured. The ratio of the cell current to the beam power is called the cell responsivity. So you use a reference cell, basically. So it is the ratio, again, QE is the ratio of the number of charge carriers created divided by the number of incident photons at a given wavelength. So QE is a function of wavelength, as we saw in the last slide. Number of charge carriers is the current divided by the electronic charge. Number of incident photons is the incident power divided by the energy of the photon. That way, as you know that way. Pn is, of course, the incident power of that way. R is if you use a reference cell, then you can scale it to that reference cell. Not so important for us, important practice. Just make sure you understand the basic definition here, because that's useful when you think about it. The instrument used for QE measurement is also not too complicated. There's some interesting optics there, so we should be aware of what it is. Usually you have let's start with the source. So there's the source right there, in this case a xenon light source. Usually fiber coupled, or in this case it's free space. You pass it through a filter wheel. Filter wheel is sometimes to get rid of any extraneous, if you have midwave UV, near UV and you want to shield the solar cell, you don't care about it, you probably put a filter. So for example, you have a chopper. So chopper is basically something which blocks the light in a periodic fashion. So it's basically a circular disc with an opening, and then it rotates. So beam passes through the opening each time the opening passes through. So if you look at the input, it goes up and down, right? At some frequency. And this is basically to get rid of noise. Because when you do these measurements, the amount of current you're going to get is very, very, very small. So use the chopper to do that. I'll explain to you what that means. Then you pass the light through a monochromator to see what that means. Basically, it's to select one wavelength because this is broadband. And that monochromator outputs a single wavelength of light, which is then passed through the cell, which is placed right there. And then you take the current, and you have a calibrated reference here. You take the current and pass it through an amplifier, which is locked into a lock-in amplifier as well. So what does that mean? That means the current that you get out will also be modulated in time. It goes up and down with the chopper. As the light is going up and down, the current is also going up and down. So you know the frequency of that. So you try to lock to that particular frequency in measurement. That means you get rid of, that allows you to get rid of any noise in measurement. Now the monochromator itself is fairly complicated, so I won't, we don't have, that's another class in itself. But just so you know approximately what it looks like. So this is kind of a very fancy, somewhat fancy monochromator. So these are two, in this particular design there are two sources. There's a deuterium source and a tungsten source. You can choose between them with a mirror. So let's say you choose this right here. There's a chopper right there. There's a filter wheel if needed. There's a slit here, which essentially allows a small narrow beam to pass through. And that is imaged using some reflective mirrors and gratings. Grading essentially splits the colors. And by moving the grading, you can select which wavelength passes out through this output slit here. Which is this, so you have these micrometer-driven slit assemblies which selects the wavelength that comes out. So this grading disperses the light like a prism. And by moving the slit back and forth here, you can select which wavelength comes out. And then this is fiber coupled. There's lots of very interesting design constraints here, which we won't have. It's a little bit outside the scope of our class. There's some details here about the optics and design of the monochromator, which are not so important for us. I'm going to skip it, but if you're interested, please take a look. The coupling optics is useful because this is related to the geometrical optics that we studied. So think about the problem that we are trying to solve here when you're building a monochromator. You're taking an extended source like a lamp and trying to couple it into a very narrow slit. The question is, how do you do this very efficiently? If you put a regular lens there, like a condenser, and not be very careful about this, you will lose a lot of light. And that's not good because light is precious. In this case, because you're trying, the more current you get, the more signal you get, the better your measurement will be. So you throw away light, you get less signal. That's not good. So usually people spend a lot of time trying to design this very, very carefully. There's lots of, and this is basically geometric optics, which we learned in the first half of this class. So you can actually do this now. You have the skills to do this. You can use light tools, by the way, to design this. Do more sophisticated tools than that, but it's the same, similar kind of principle. And this is important because if you look at what the slit does, is that it basically takes and projects the beam onto a grating. And the spectral resolution, or how precisely can you select out a wavelength in the monochromator, is directly proportional to how big of a grating that you can use. The bigger the grating you can use, the more precisely you can pick out the wavelength. The smaller the grating you use, less precisely you pick out the wavelength. What that means is that if you want to do this plot here, these points, you can see, if they are too far apart, sometimes you may not see all the physics that's going on. They will be too coarse. So you need to be careful how those are designed. I won't go into the details, not so important for us, but just be aware that this is it's a critical design parameter in this instrument. Now, just also be aware that the different solar cells have very different responses. This is similar to the spectrum splitting lecture that we saw. This is the solar radiation. This is different solar cells. So this is amorphous silicon. The response is right there. This is gallium arsenide, and this is the CIS, or cadmium sulfide. So you can see they are very, very different because there are different band gaps, there are different crystal structures, and so on and so forth. So the instrumentation that you use is usually not general purpose. General purpose means it's not good. Usually you have to select it based on the cell that you're interested in measuring. Something to be aware of. Okay, so that, let me actually stop there for a second. That somewhat finishes the first part of the lecture. So we're going to take a short break while I set this up, and let me stop the video first and then